Hello and welcome back. This is day 3 of Advent of Code. Um, so let's see, it's almost 8 in the morning here. I didn't get the chance to record this last night. Sometimes real life gets in the way. Um, but yeah, we'll continue with the problem here. Before we get started, I want to give a shout out to my man Jay Fode. Jay was the CTO of Dyalog for I think like 8 years, quite a while. He doesn't work there anymore, but last year, 2018, he did a bunch of Dialog solutions. He has a repo for 2018 as well. And actually seeing his solutions for 2018 is what inspired me to pick up APL in the first place. So yeah, check it out. It's awesome that he's doing 2019 as well. He has a problem 3 solution, which I haven't looked at yet. I'm sure it's awesome. But if you look at just like his problem 2 solution, if you remember from my last video, my problem 2 solution was really, I mean, it's pretty imperative in nature. I have like some global variables. I'm basically using an error guard as like a try catch block. I mean, it's kind of hacky, and it's roughly equivalent to something that you might write in like Python or something. But Jay's, day 2 solution, this is quite elegant. So he sort of avoids index errors by using the take operator here. He's using a recursive function. Yeah, this is sort of emblematic of something in APL we call like array-based thinking. And it's something, so I have a day job, writing imperative codes. And so trying to sort of transition to thinking about solving these problems in an array-based manner, playing to APL strengths is sometimes difficult, especially yesterday when the problem is something that I would normally solve in an imperative manner, like like implementing a VM or whatever. But J's solutions are consistently good, consistently demonstrate array-based thinking. So I would recommend you to check them out. Unfortunately, as far as videos are concerned, you are stuck with me. Oh, actually, Jay did a webinar last year about his experience doing the 2018 Advent of Code, and I will link it in the description. It's a pretty good video. All right, so we are on day 3 here. Now, I confess that I looked at this problem last night. I couldn't help myself. So I'm not going in totally blind. I haven't written any code yet. But I like this problem because I think that this is basically the first day where we can sort of have some fun and start doing some like array-based solutions to the problem. Right, so my plan for this is basically, so we have wires coming out of some origin, they snake around the XY coordinate plane, and we are finding the closest point where they intersect as measured by Manhattan distance. So my plan for this is basically I'm gonna parse the puzzle input. I'm gonna put together 2 giant lists of XY coordinates, and we'll figure out the intersection between those 2 lists and then take the minimum Manhattan distance. There's probably something fancy you can do where, I don't know, where you can like store the different sort of intermediary XY points, and then maybe use a more analytical method to figure out where the intersections are. This is basically like brute force. And I think, so if I look at the puzzle input, we are going to be putting together, I think just looking at this, the areas are going to be pretty large. probably, I don't know, between 100,000 and 500,000 elements. But APL should have no problem working with arrays of that size, I'm pretty sure. So before we take the standard puzzle input, I'm just gonna start with the test cases. So let's see. So let's edit po3.text. Yep. Okay, great. And yeah, we will. Let me say file to disk. I think in RIDE there's no like save button, which is kind of annoying. And then we'll edit po3.dialog just to get ourselves set up. Yep. Okay, great. All right. Well, let's dig in. So here's my plan. Basically, first of all, we have 4 directions that we can move in: right, down, left, and up. And each one of these directions can be represented by an offset in x and y coordinates. So in order to get those directions, the first thing I'm going to do is I'm going to take the equal Cartesian product of iota 2. This is an idiom that we use in APL to basically get an identity matrix of any size. But for a 2-element identity matrix, we have the first 2 directions right here. So 1, 0, you can think of this as up, I guess, and 0, 1, you can think of it as right. And then to get the other 2 directions, we can take right tack laminate minus. Yeah. And then, right, so this will be like up, right, down, left, something like this. And then we'll break those apart into separate elements, and we'll assign this to D for direction. Cool. And let's start parsing some files. So there's this CSV operator, which I actually just learned about yesterday, looking at some other solutions. I've been using ingit for basically everything. But CSV is pretty nice, should save us a couple characters. And so if I do down like this, no, not PO2, sorry, PO3. Invalid number of fields in record 2. Really? So you say. In record 2. Oh, it's I guess CSV doesn't deal with jagged arrays. So because these lines are different sizes, basically APL doesn't like matrices of uneven size. So all right, well, that's too bad. I guess we will go back to using ingit 1, and we will do the same thing that we did last time. So we'll take the first one so that we get the actual content, and then for each row we will split it apart. So we are splitting on comma, and then I think that it is let's see, not equal. Yeah, not equal right tack like this. Yeah, okay, great. And this will just give us lists of our input. So we'll start building our solution here. We have P for our input, and we have D for our directions. Cool. And then basically what I want to do is for each P, for each W. Let's see. So I think that what we are gonna do, let's take the first element of W. This should be the letter that specifies the direction. And we'll do index of that direction in the string. So for our directions, let's say that this is up, right, down, left. Yeah, up, right, down, left, like this. So what we're doing is we're translating the letter into an index, and then we can index into our direction array, so that'll translate there. And then what I'm going to do is I'm going to reshape, basically going to create a bunch of elements of this direction in a 2-column in-row matrix. So what we'll do is we'll do one drop W execute to append, like this, basically. Let's just hang on. So before we do this on each P, each W, let me just try this on, let's say like R10, something like this. Okay. This is not quite what I was looking for. I think I have to disclose here. Yes. Yes, very good. Okay, cool. And now, let's say that we do for each W, for each P. We have to be careful. So I think for this test case, it's probably okay. But in general, when data starts to get like super large, it's going to be slow getting back to the interpreter. Not because the calculation is slow, but just because like the interpreter has to display a bunch of data. Anyway, for this test case, it's fine. So, and then what we want to do is here we want to do, I think, laminate reduce. Yeah. So that we just get 2 giant arrays, right? And then once we do that, let's disclose it, right? So we have the arrays themselves, and this is what I'm getting at. This is why we're doing these big, these like arrays. So we can do basically a path is equivalent to a scan of the addition function. So like we're adding down the matrix, vertically, and we're keeping the intermediary results of each addition. So yeah, we'll get something like this, right? So if we look at P, we have right 75. So we would expect to like move, we would expect to have 75 elements here. And we just sort of add them all together, right? And then, same thing for like down 30. Once we start as 75, I don't have, can I, all right, fine. Let's turn rows off. Well, sorry. Fold equals 0? Off? What's fold 9? Okay. Yeah, all right. So I mean, this will be a big list, but yeah. So the idea is basically, so we have right 75, D30, right? So right 75. Yep, and then we're moving down, so we'll move the x coordinate. Then we go down to 30. The next one is probably like right 83. So 83, 75. That'll take you to 158 here. And then we're moving left, it looks like. Right? And the same thing for the other column. So, well, let me turn back. Rows fold equals 9, so that we can actually do some stuff here. Yep, okay, great. And let's say, well, we're going to break these apart into sort of XY coordinate pairs, like so. That's going to be a long row, but that's fine. And then let's say that we do an intersect reduce between the two pairs. So intersection is just going to find the elements that exist in both lists. Something like this. Yes. Excellent. We'll disclose that. And we'll put it into a matrix like so. And I think the Manhattan distance, so because in this setup, we're basically measuring the Manhattan distance from the origin. So 0, 0. So that makes the calculation pretty easy. I think it's basically just like absolute value sum along, sum horizontally, sum each row. And then we will find the minimum, like so. The answer is 159, which is correct. Hey! All right, cool. Let's try. Well, okay, so before we continue, let's just say, this will be our part 1. And we are probably going to have to refactor this for part 2, but that's okay. So let's try our second test case here. We should get 135. Yeah, save changes and return. Only save file to disk. Cool. 135, yeah. Okay, great. And the nice thing about operating on big arrays like this is that it plays to APL strengths. I mean, these primitives are optimized to work on very large arrays. So I think this should be relatively fast. All right, so let's edit p03.text, and we'll get our puzzle input. Cool. And we will paste it here. Only save file to disk. Yep, great. And yeah, cross your fingers. 860, it tells me. Well, let's find out. Hey, very nice. Very nice. Part 2. Very timing sensitive. You need to minimize the signal delay. By the way, so if I've learned anything from previous days, I'm going to take my time here and actually try and read through the problem. So we're minimizing the signal delay. Calculate the number of steps. Choose the intersection where the sum of both wires' steps is lowest. If a wire visits a position on the grid multiple times, use the steps value from the first time it visits that position. Okay, I think I'm going to use index of here. This sounds like the default behavior of the index of operator or function. Number of steps a wire takes is the total number of grid squares the wire has entered to get to that location, including the intersection being considered. Okay. The above example, blah, 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 20 steps. Total of 30 steps. Here are the best steps for the extra examples from above. Okay, no problem. So I think basically what we can do here is let's refactor things a little bit. So we are going to say, we can just assign this to like x, and this will be our processed, data from the input, right? And x is, well, yeah, there's only 2 elements, but like if we look at the first one, there's, yeah, these lists are pretty big, so it's over 150,000. Cool, and then we can say, so we'll say that this equals x, and then part 1 is basically these operations on x, and this should give us the same answer, 860, that's cool. And so we'll edit po3.text once more to get our test cases back. Let's say file disk, blah, blah, blah. Okay, so, and now, if we calculate x for this, let's see. Yeah, so tell me x, we have a bunch of this stuff. We still want to know, all right, so we still want to know the intersection between them, right? So we have these, if we disclose that, we'll just get the, and what do we want to know here? So for each one of these, for each list in X, we are trying to find out, so this will be like W, we are trying to find out alpha index of W, which can be written easier as just W jot iota. Yeah, what does this give us? Oh, that is not at all what I wanted. So it's the other way around. Yeah, like so. Okay, great. And then for each one, yeah, for each element x, we're doing this, and we want to sum them. Well, no, that's correct. Each one is the count, like this. Okay. Hang on a second. So what am I doing here? Okay, let's go back. So we take the first element of the intersection of x, like so. That's cool. And then we want to find, so index of will give us the number of steps that it took to reach this point from each element in X. Okay. So why am I getting these like 2 numbers here for index of? Right? Let's just say that I take like the first element of P, and I say index of, this stuff. Yeah, see, this is, wait. First element of P. That doesn't seem correct. Oh, geez. Yeah, sorry. First element of X. Still drinking coffee, folks. Okay, cool. So first element of X, like this. This is what I want, right? And then yeah. Yeah. So for each X, index of W. Maybe I can do. Yeah, I can probably simplify. Well, all right. Let's just say that we take the intersection of X and we supply this to an anonymous function like so, and we'll say for each X, we are. What are we looking for? We're basically looking for W index, W iota alpha. I know this is not like super efficient, but yeah, see, I want something like this. So why couldn't I get that? All right. So this can be simplified like so. Yep. And if we add them, we'll get this. And then we can disclose it and take the minimum, 610, which seems to be the correct answer. All right. Second case. So we'll do po3.text. Yeah, there's probably some expert in RIDE is going to tell me that, hey, there's an easy way to save text files. That's probably true. All right, so we'll say that this is part 2. 410. It is indeed 410. And I still get the right answer, 135 for part 1. Alrighty. Well, let's get our puzzle input. We're passing our test cases. I'm feeling optimistic. And so if I copy this, put it over here, 9238, and it's pretty fast too. Very nice. All right, I like this puzzle. I like this puzzle because I think that it plays to APL strengths a little more than the first 2 days did. So yeah, here we're basically doing a bunch of area manipulation. You know, we're trying to operate on as large areas as possible. And so APL, you know, it's conducive to APL, and it's quite fast as well. So let's see. If I were to shake this out, how would I optimize any of this? For each x, I mean, I can maybe, I'm calculating the intersection here, so I can probably do like, you know, I can assign I, and then here I can use I instead, right? Yeah, this is min plus, I think, $860, $92.38, still the right answer. Yeah. What else? There's quite a few for eaches here. So I thought about using a reduce instead. I think for each here is probably fine. Yeah. Okay. I think this looks good. I would be happy shipping this. Oh, this is I think we can simplify this slightly. So we can do comma jot this thing. I mean, I think. Yeah. Yeah. Okay. Okay, cool. Yeah, I'm gonna ship it. Awesome. Thanks for watching. Hopefully the future problems are also sort of conducive to this area-based manipulation, because that's, you know, that's the most fun for me. And hopefully it's fun for you to watch. So thanks for tuning in, and I'll see you next time.